Take a statement like, if you drop your phone, then it will break. The truth value of that statement depends on the truth value of the component parts. You dropping your phone and it breaking. We're going to evaluate the truth value of a statement in terms of its component parts, and as an example, we will use a statement by a politician.
It will change. We will have so much winning if I get elected that you may get bored with winning. Believe me.
Now we're going to check the truth value of that statement, but under 4 different circumstances. Let's break down what he said. We will have so much winning if I'm elected president. That is, the statement A is Donald J. Trump is elected president, and B is we will have so much winning. Then we're saying A implies B, or if A, then B. So let's consider the 4 cases that could determine the truth value of the statement. Either he is elected or he is not. Either there is so much winning or there is not. In the first case, Donald J. Trump wins the election and there is so much winning. In that case, he did not lie. He told the truth. In the second case, Donald J. Trump is elected and there isn't so much winning. In this case, what he said was actually false. He was elected and there is losing. So this is a false statement. But what about the other 2 cases? What if he was not elected and there is so much winning? He made a statement about fulfilling his promise if he wins. So we say that he told the truth. And if he wasn't elected and there isn't winning, he still didn't lie. His statement is true because it's not false. And there are only 2 cases here, either true or false. We're going to look closely at this by saying if A then B, and then we're going to assume that B is false. In this case, we're not in the 2 rows where B is true, and we're not in the row where if A then B is false. That means that we need to be in the row where both A and B are false, and if A then B is true. In that case, we can conclude that A must be false. And so what we've derived is if not B, because that's what we assumed, then not A, because that's what we concluded. If that's the case, then we can also switch these 2 statements and derive the one from the other. They end up being exactly equivalent. One is called the contrapositive of the other. Let's give a short example of a proof of an if-then statement. We're going to show that if n squared is even, then n is even. This particular statement is much easier to show. We show the contrapositive. If n is odd, then n squared is odd. If n is odd, then n is equal to 2k plus 1 for some integer k, and that means that n squared is equal to 2k plus 1 squared, which is 2 times an integer plus 1. This implies that n squared is odd. Now we've shown that if n is odd, then n squared is odd. We can conclude that if n squared is even, then n is even.